Hi, and welcome to today's webinar, Analyzing Composites Using Finite Element Analysis, and this is part 1, Composites in Femap. My name is Alexander Karen. I'm going to be taking you through today's webinar. I've worked for FEA for over 2 years now and have my master's in science from Virginia Tech in aerospace engineering. So with ever-increasing use of composite materials in manufacturing, the need for good analysis tools to help in the design of composite materials is becoming more and more important. There's various capabilities to help you quickly view and understand an existing model or create a new one. Layups can be viewed diagrammatically with the layup viewer and using the layup editor. The laminate definitions can be created and edited easily. With the idealization of composite structures, Plie discontinuities due to drop-off create situations in the finite element where we have adjacent elements containing differing number of plies. We can visualize and post-process this using Femap's global plie tool. Global plie IDs can be assigned to individual plies for each laminate, and we can then review those results for those global plies across multiple laminates. So now we're going to start our live demo for today, and we're going to switch over to Femap. So as you can see here, we have a basic wing model. The wing model is contained, has an upper skin, a lower skin, a spar, and a couple ribs. As you can see, we have multiple property regions throughout the spar. So the first thing you're going to want to do is when you're creating a new model with layups is you're going to set up your materials. So we're going to go and we can see we have 3 materials in this model currently. We have a fabric material, we have a unidirectional tape material, and a foam core material. So now if we go in and we look at these, your typical ply materials are going to be 2D orthotropic. So we have our stiffness in the 1 and 2 directions, our shear and Poisson's ratio. Now something that we need to fill out in the material part in order to get results, failure indices for individual plies is we need to set stress and strain limits. So as you can see for this material, we have strain limits in the 1 and 2 directions as well as shear direction. So if we go to our unidirectional tape material, we could see that the 1 and 2 directions of this one are different because it's not a weave. Another thing to note is that in the 2 direction, we've just set a large number for the stress limits because we're not looking for failure in those directions if the fibers aren't running in that direction. And we can see we have our core material here, and we're not looking for failures in the core current for this model, so we've just set those to a high number. So now that we have our materials, we're going to go into our layup definitions. Now this is where you're going to be modifying and editing your layups. So our first layup is our wing skin, and as you can see that's applied over the wing skin areas. But we have different layup definitions for where the wing skin overlaps the spar. So if we go in and we edit our wing skin layup, this is our layup editor. So we could see for this we have 3 plies for this layup. We have 2 plies of the fabric and 1 ply of our core, and you can see we have our thickness and our angles set here. Now if we wanted to go in and add a new ply, we could just go in and we could set our material. So say we wanted to set a fabric, and then we wanted to know another same thickness, and then another 45. We can create new ply. So now we have a new ply. So we made this from a 3-ply layup to a 4-ply layup. So now if you say you put a ply in the wrong area, you can actually go in and just move it down or move it up, depending on where you want to move your plies. You could also go in and just edit materials, so you could swap out materials very easily or change thicknesses. So you could just go in and then say, update thickness, update material, and that changes right on the fly like that. So let's delete that ply. So another thing you could do while you're in your layup editor is you can actually view the layup in the layup viewer. So you can see it lays out the layups for you, and you can see we have our 45 ply here of our face sheets, and then 0 ply of our core material. And you can show it with the thickness in relation to each other. That's a good way of just viewing and making sure your layup looks correct and matches what you put into the layup. Now, another tool that the layup editor has is the compute button here. So if we hit compute, Femap will then go in and calculate equivalent properties for that layup. So it'll give you in-plane properties, so your EX, your EY, your GXY, as well as your news and alphas if you had those on your material cards. It'll also calculate your AVD matrices as well as their inverses. So that's a very useful tool, say, if you wanted to convert your layup into an equivalent P-shell or something like that. So now we can see we have our other layup regions. So we can go in and we can take a look at those. So this area is where the wing skin overlaps the spar. So for this layup, as well as our other layups, we have set up global plies. So now we set up our global plies so that we can set up consistent plies over multiple layups. So as we can see here, our first 2 plies are actually the wing outer space sheet and the wing inner face sheet, and the core was pared down for where it's connected to the spar. So that even though our first 2 plies are the wing skin plies, they are actually global ply 1 and global ply 3. So this helps with our post-processing when we want to look at results and things like that. So if we go in to our global ply editor, we could actually look at and see where our global plies are located. So we can show our wing skin outer face sheet. We can see that continues over the spar. And if we show our core, we can see that it doesn't continue over the spar. And same thing with the inner face sheet. And then the spar plies. You can see that the spar plies just continue down. So now we set up multiple regions for the spar because it tapers as it goes out. So we could see that not all of the interior spar plies continue out to the wingtip. So if we go in and look at the, say, the property that's out by the wingtip here, we could see that we removed some of the interior 0 plies so that the 7th ply, say, in the outer area, the outer layup region, is actually the 12th global ply. So this global plies is really helps you stay consistent in which plies you're looking at in the model. So now that we have all of our layups here, we go into and we update our properties. So we have a property for each layup, even though you could have multiple properties referencing the same layup. So if we go in and we look at our property for this laminate element, we can see this is where you define which layup is being referenced by that property. Now, one thing to note here is, in order for Femap to spit out failure indices, you need to make sure that 2 things are filled out in this property part. So you need to set a bond shear allowable, and that's your allowable between your face sheets. And then you also need to pick a failure theory. So for this one, we selected Hoffman. So now that we have both of these filled out, Femap will calculate failure indices for the plies. So for this model, we set up just a simple pressure load that's located on the lower surface of the wing. We can see our pressure load distributed here. And we just set up a constraint at the root of the wing. And we set up a simple static analysis. So we're just going to run this analysis. It should be finished here in a couple seconds. So that's finished. So we've got our results here. So let's go into our post-processing toolbox and look at these results. So we turn on our contours. So the first thing to note here is that Femap has spit out an output vector called laminate max failure index. So that's the 6060 output vector here. And this displays your max failure index based off of the failure criteria that you set on your property for all plies on your model. So this shows the worst failure indice in any ply across all your laminate elements. So in addition to that, you could actually go in and view ply by ply results. So as you can see here, we can go in and look at the laminate ply 1 fiber failure index. So if we click on that, that'll be the failure in the first ply for every layup. So then we can click through some of these and say we go to the laminate ply 4 fiber failure index. So we view that, and then we change our color width to element colors. So we can see that it's only outputting results for laminate elements that have at least four plies. So if you're looking at a specific fiber, you may not want to view results for the first ply in every laminate. You may want to look at a ply that's consistent across multiple laminates, but the number of that ply in different laminates varies. So in order to do that, we can go into our output vectors and we can select our laminate ply 1 fiber failure index. And then we can go into our laminate results from, and we could select a ply that's based off of our global plies, so our wing skin outer face sheet. So now we could see that it is showing results for just this global ply, and we could see that it's continuing across multiple laminate pieces, and it's not showing results for any elements that aren't included in that global ply. So we can go through and we could see the spar results. And we can see that if we go to, say, our spar ply 4, that ply doesn't continue all the way out to the wingtip. So now the results that we are viewing are failure indices. And if we see a failure indice over 1, we know that there's failure. So as you can see here, we're just showing a failure indice of 0.74, so this isn't failing currently. So that's good. So that about sums up our live demonstration for today and shows you some of the capabilities that Femap has in handling composites and composite materials.
Alex, I don't know if you can get to the questions. I can start reading them and answering the ones I know. So the first question I see is any factor of safety built into the failure index, and the answer is no. The allowables that you enter into the software have to match the load you entered into the software. So if your structure or the loads on your model are at limit load, your allowables also have to be entered at limit load for the failure index to calculate properly. If you enter your loads at ultimate load, then your allowables would also be at ultimate load for the failure index to calculate properly. Alex, you want to go?
Yeah. So the question is, how do you model transition areas, i.e. from thick areas to thin areas? I'm thinking mainly honeycomb panels that have a thick center, thin edges, and tapering to transition areas. I mean, it'd probably depend on the quality of your model. You could just have varying property regions where you transition your honeycomb thickness down over multiple elements down to your thinner region. So you'd have multiple layup regions, and your layup regions would have progressively thinner and thinner honeycomb down to where you transition to an area without any honeycomb.
And somebody asked if they could have a copy of the PowerPoint. Yes, it's up under handouts. So you can have this entire PowerPoint. There's even a couple of backup slides that could be useful to people. There's a detailed definition of how the failure index itself is calculated and how to calculate a margin of safety. We're using Hoffman as an example today. That's all in the backup slides and what's been uploaded. So Dave Harvey asked, can we give some detail on the different failure theories? Dave, at the more of a higher level question, but basically Hoffman and Cy Wu, and there's one other, Cy Han, I believe. Those three are really the Cy Wu theory. And if you know anything about Cy Wu theory, there is one variable in his theory that he couldn't come up with a way to analytically determine. So he had to run a test to find the last value. And Han and Hoffman have come up with ways to estimate that last value. So Hoffman, you can do the entire equation based on the data you would know without any test, and same with Han. Then there's also a max strain failure theory, which isn't. So if I go forward into the backup structure, you know, the Hoffman failure criteria is an ellipse type failure envelope. Max failure theory basically is a square, and is used occasionally depending on what your layups look like.